So we're now going to continue from question number 3 in this same paper for mechanical level 3, properties and strength of materials for April 2025. So in the previous video, we already did the first 2 questions, basically as part of our introduction. So we now have to finish up the other remaining questions, at least see how far we can move. So we go straight to question number 3. To move faster, I'll just do this. And I'll flow straight to the third question. I believe it's this one. Yes. Question number 3 says, state 3 forms of heat transfer. State 3 forms of stress that are likely to arise in a cylindrical material. So 3 types of forms of stress that we're likely to expect in a cylindrical material. Now, this one is specific. So we have the first one, which is hoop stress, or it can also be referred to as a circumferential stress. We also have the longitudinal stress, or we can also call it the axial stress. And lastly, we have the radial stress. Already telling us the orientation that this is supposed to be along the radius or the thickness of the cylinder. So this is how the 3 are arranged. Now, part B is a continuation. It says, describe the stresses, those stresses we've just talked about in air. We're required now to describe them. Describe the stresses stated in air above. So hoop stress, start with hoop stress, the circumferential one. So this is the type of stress acting along the circumference or tangentially to the cylinder that you are analyzing. So here, it's normally felt like the kind of pressure where the internal pressure is normally pushing outwards from the cylinder. And of course, it's normally along the length. We also have the longitudinal stress. The longitudinal stress, this one is the one that acts parallel to the axis of the cylinder. And of course, here you see, because we're dealing with a cylinder, this kind of stress will therefore act along the end caps of the cylinder. Lastly, it's the radial one. This is the one I tried to talk about, that actually it's along the radius, meaning the stress normally acts perpendicular to the curved wall, or simply along that radius of the cylinder, so away from the other 2. Now this one, you notice that by nature, it's a compressive stress because it will try to compress the thickness of the cylinder as the pressure inside there acts outwards. Here's our question now, continuing from there. A cylinder, let me just realign this because it's too close to the wall. A cylindrical thin drum, 1,200 millimeters in diameter and 4 meters long, is made of 20 millimeter thick plates. If the drum is subjected to an internal pressure of 0.5 megapascals, determine the changes in diameter and length. Take E, or Young's modulus, as 200 gigapascals and Poisson's ratio as 0.25. Let's try to look at information we have been given with, or we have been provided with. First of all, the diameter D is 1,200, and as per tradition, we're not going to use the millimeter. We convert this to meters just by dividing by 1,000, meaning this will move 3 decimals, and we end up with 1.2. So the diameter there is 1.2 meters. Then we also have the length, 4 meters. The thickness of the plates, that's 20 millimeters. So again, we convert the 20 millimeters to meters, meaning the 20 divided by 1,000, we end up with 0 0.02. Then additionally, we've also been told that this cylinder we're dealing with is subjected to an internal pressure of 0.5 megapascals. So then let us determine the change in diameter and length. Take Young's modulus as 200 gigapascals, Poisson's ratio 0.25. So meaning that here when we continue, pressure 0.5 by 10 power 6, then Young's modulus is 200 giga. So giga represents 10 power 9. Just like our mega here, it's 10 power 6. Last is Poisson's ratio. Now this Poisson's ratio, in this case, we represent it like that. Or you can also say that your Poisson's ratio is mu, and then you indicate what number it is. 0, in this case, 0.25. So that's our Poisson's ratio. And basically, that's about all the information we have in this question. And with that information, can now get to the solution. Let's start with the circumferential stress. The stress along the circumference is given by this formula, PD over twice the thickness, PD over 2T. So this is the formula we use. And along that, we substitute. First, P is pressure. This is the one, 0.5 by 10 power 6. Then we have the other one, which is the D. The diameter of this cylinder is actually 1.2. And then 2 is just 2 like that. Then the one that we're dealing with now is this one, 0.2. The 0.2, 0.02, that is the thickness. And we leave it like that. So then, when you compute all these, enter this in your calculator, we are supposed to get this number here. Just a quick minute, is it? Yeah. Yeah, so when we compute that, what we should get is this. Our answer is this. 1.5 by 10 power 7, 1.5 by 10 raised to power 7 pascals. It's like simply saying 15 million pascals, 15 million newtons per square meter. Let's make progress. The next thing we have is the longitudinal stress. The longitudinal stress, the same formula that we have earlier, but this time around, what we are going to have is PD over 4T. The only difference is this inclusion that you're seeing here. We, instead of having 2, we now have 4. The rest remains like that. So we still have the P, the D, then over 4T. The pressure is this 0.5 by 10 power 6 as usual. The diameter is 1.2. Then, of course, we have our 4 there and the thickness, which is 0.02. Okay, now, having substituted like that, we end up with our answer, which is just 7.5 by 10 power 6. This one is now our longitudinal stress, Then moving on, we need the circumferential strain. Because we already have the circumferential stress, it's only natural that we can now calculate the circumferential strain. So what do? We invite the formula for Young's modulus, and then we just try to balance it up a bit because we're dealing with a cylindrical member. So what do we have then? First of all, the circumferential stress is given by this expression. First of all, circumferential stress is equal to stress, or the circumferential strain is equal to circumferential stress divided by Young's modulus. But we don't end there. We say minus the counterpart, which is the longitudinal stress over Young's modulus, but we also multiply by 1 over m, which is basically Poisson's ratio. Now, when you look at this expression, we might as well make it smart because 1 over the e is common on both. So we can factorize 1 over e inside the brackets. Here, we are going to remain with this circumferential stress. So this is the one we have there. Minus, so the minus remains. And then lastly, we have Poisson's ratio multiplied by the longitudinal stress. Then, of course, we can now just do the substitution. We have, first of all, 1, or we start with the 1 over 2, 1 over e. So 1, our e is the Young's modulus, which is 200 by 10 power 9. Then open brackets, we have circumferential stress, which is 1.5 by 10 power 7. Yeah. Then added to that, we also have this, sorry, just there. We also have this one. And this one is our Poisson's ratio, 1 over m. 1 over m being represented by this. So by introducing this, we have substituted for 1 over m, this one. Then what about the longitudinal stress? The longitudinal stress is here, 7.5 by 10 power negative 6. So we substitute it there. Hence, this is what we have there. We have 7.5 multiplied by 10 raised to power 6. Now, as usual, when you do the computations, you'll find that your answer will therefore end up being 6.6, rather 6.5625 multiplied by 10 raised to power negative 5. One thing we mentioned was that strain doesn't have units. So the way we've done it, it means we've arrived. We leave it there like that. That's our answer for circumferential strain. Circumferential strain. Can we repeat the process, but this time around for circumferential, rather longitudinal? Let's go for longitudinal. Now, or before we even do that, let's complete our working. First, using the circumferential strain, we're able to find the change in diameter, because the circumferential strain equals the change in diameter over the original diameter. So we just go ahead and substitute. But if you want, you can decide to make change in diameter the subject of the formula. But in this case, we're just going to do the substitution so that our progression there, we don't have to waste a lot of time. So it's substituting. First, we already found that our circumferential strain was this 6.5625 by 10 power negative 5. Then this change in diameter is still stubborn. We don't know what it is, so we leave it. Divide by 1.2, which is the diameter. Now, the task we have here now is simply to cross multiply. We're going to multiply the 1.2 by this strain that we have right here. So then our change in diameter therefore becomes 7.875 times 10 raised to power negative 5 in meters. So with the circumferential strain, we found the change in diameter. Now let's use the longitudinal strain to find the other change in dimension, which is the length. So here, we can straight away go for that. The longitudinal strain. Now, one thing you're going to notice is that when you inspect this formula carefully, they have just exchanged. The longitudinal stress, the strain rather, is equal to longitudinal stress over Young's modulus minus circumferential stress divided by Young's modulus. Then we're multiplying by Poisson's ratio, which is 1 over m. The first one that we had, this was actually here. Let's do the highlighter. This one was here because that was the one we're dealing with. In this case, we're dealing with the longitudinal stress, so it's the one that is supposed to be here. Then again, we're just doing the factorizing. 1 over E in the brackets, longitudinal stress minus 1 over m times circumferential stress. Moving on, the longitudinal stress, therefore, we now just do the substitution. 1 over our E is 200 by 10 power 9. Then 7.5 times 10 power 6. This is longitudinal stress. Sorry, this is Young's modulus. Then here, longitudinal stress is 7.5 by 10 power 6 minus what we are calling as 1 over m is here, 0.25, multiplied by the circumferential stress, which is 1.5 times 10 power 7. So with this combination, what we're now going to have is the final answer here, which is 1.875 times 10 raised to power negative 5. But we don't end there. We also say, let's find, let's get that, okay. The change in length. So we are going to invite the original formula that determines the definition of change in length, which is longitudinal strain is equal to change in length over the original length. Longitudinal strain is equal to 1.875 times 10 power negative 5. However, this one we don't know, so we leave it as change in length just like that. Then the original length is 4, so we leave the 4 there, no problem. Then after that, making change in length the subject of the formula. Sorry, not this one, where this can go here. All right, making change in length the subject of the formula. Sorry, not change in diameter, but change in length. When you multiply, this one we are calling as 1.875. Then you end up multiplying that by 4. You end up with this 7.5 by 10 raised to power negative 5. So the only thing is this is just a typo, which is very simple for us. Let me just do the needful. We're saying this is not supposed to be change in D, but change in length. So let me quickly write it the correct way right here so that you don't end up mixing them up. Okay, there. Okay, so this is actually change in length. Okay, and boss, our answer is 7.5 by 10 raised to power negative 5. Question number 4. Draw the shear force and bending moment diagrams using the figure provided below. Indicate the point of maximum bending moment. This is the diagram being referred to. You can see that this diagram has a combination of a UDL and a moment. We don't even have a point load directly acting on this load. However, the way it is, it can be quite cumbersome to proceed just like that. There's something we need to do about this. This one is straightforward because this is just a UDL. So with that in mind, let's redraw this same diagram respecting this one. Now, the first thing I want you to notice that when you look at this diagram here, pick a number. You can see the perpendicular distance on this at point C is 0.5 going up to where the 1 kilonewton force is acting. So meaning that there is a localized moment arising from this behavior here, which is the product of this one and that perpendicular distance. In other words, we are saying 0.5 meters multiplied by 1 kilonewton. Sorry, let me just make it the right way. Giving us a moment of, because when you multiply 0.5 by any number, you end up with the same 0.5. So this is what you have. The 0.5 kilonewton meters is a floating moment. Rather, it's a moment that is going to act at point C on its own. And it will definitely be considered just like that. So 0.5 kilonewton meters is the one we're going to put there. The rest of this here, deal with them one by one. So let's redraw now to take care of this, to include this one that is acting at C. Here we are. We said 0.5 kilonewton meters. This is where it is acting. So there we've put it. We have our UDL here. We have our reaction at B. We have our reaction at A. There's C and there's D. So what are we going to do then? Let's now start by taking moments about B, meaning we're going to take moments about here. Condition, summation of clockwise moments supposed to be equal to the summation of anti-clockwise moments. Having established that, then we can start now looking at the moments that we have. First of all, this one, this is a clockwise moment. At the same time, when you look at the moment that we're going to create as a result of this, what do you call this? This UDL about there. This will behave in such a way that the whole distance that we have from the whole distance that we're having, oh, sorry, just, yeah. Okay, yes, thank you there. Just a minute. So I think it's this one. All right. So the distance that we have where the UDL is acting is from B to D is 0.7. Now, this 0.7, the UDL, like any other uniform member, it always acts at the center. Meaning, to get the force, we are going to multiply this distance by that, the UDL force per unit length. So 5 kilonewton per meter times 0.7 meters gives us the force. But as we're taking moments, that's not what we want. We want also the leverage, the perpendicular distance. So meaning, why not then include from the center to there? So that distance. How much is that distance? This is the one mentioned here now. It is 0.7 divided by 2 because we've said that for any uniform member, for the UDL, for the uniformly distributed load, it will always act at the center unless it is the other type which is varying or a stepped one. But this one, which is uniform, balanced like that, it will always act at the center. So 0.7 divided by 2. Then this is constituting our force. Added to that, we have this other clockwise moment. Then on the anti-clockwise side, we have RA, this one, times the whole distance. What is our distance? Our distance is In fact, I can even put it like this. For the other side, we can say it is RA multiplied by, first of all here, 0.5 plus 0.8, again plus 0.7. When you do that, you notice that it will be RA times, in fact, we're still saying the same thing, it's the same A. Oh, this is just the same A. RA, or reaction at A, multiplied by this added together, 0.7 plus 0.5 gives us 1.5. 1.5 plus 0.5, the total answer is 2. So that's why you can see that here we've written RA times 2 meters. Now from there you compute, make 2 the subject of the formula. The end result is RA being equal to 0.8625. That is our reaction we have just calculated. To find the other calculation, we are going to just say summation of upwards forces is equal to summation of downwards forces. What are the upwards forces? It is RA, which is this one, plus RB, this side. Now we know RA, we already found it as 0.8625 plus RB is equal to the uniformly distributed load, which is 5 times the whole 0.7. Just dealing with forces. When you say 5 times 0.7, these meters cancel out, then you just remain with the force because in this case, we're just dealing with forces. From there, our answer is 2.6375. Now, I have to emphasize here, while we were taking moments about B at first, to find the other reaction, you may decide to take moments about A, this side. The answer you are going to find is this same one here, which is 2.6375. That's our RB. Or you use what we've done here. The result is the same. Then we invite now the shear forces. First of all, the shear force at A is 0. Now with this UDL, things are a bit interesting. From D to A, we are having just one value, so we add them up. The reaction, which is positive 2.6375, minus the UDL, which is 5 times 0.7. Our answer is negative 0.8625. The bending moments, for the bending moments, in fact, let me invite this diagram here so that we're able to follow through with it. Just here, just a quick one. I bring it here so that we don't have to start wondering where it is. So as for the bending moment, just do this and you put it there. Also this there. Okay, there we go. Oh, sorry. Here. Okay. So this is what we're dealing with. Let me just put it back in our screen. This is what we have. So we're now on bending moments. Moment at A, 0. Then moment at B, I think this one shouldn't disappear. Aha, there. So first of all, the moment at A. Okay, good. We said it's 0, but when you come to D, which is this point, the point here in the middle, you will find that in that case, when you are here, the total moment will be as a result of what has remained on the left. And what are we going to have? We have, first of all, this UDL, which is 5 multiplied by 0.7 multiplied by half of it. But at the same time, we also have the reaction at this point, which is 2.6375, multiplied by the whole of the distance, because we are dealing with point D. So reaction at this point, reaction at B times 0.7. This other UDL is minus because it's acting downwards. So negative 5 times 0.7 times half of this, half of 0.7. And once you compute, you have 0.62125. Let's move to point C. Now, point C is very special. First, it has the moment where we don't include this floating moment, the moment which is acting at C, but just deal with all those remaining on the left. So what are we going to have? First, we'll have 2.6375 times the distance from here up to there, which is simply 0.7 plus 0.8, giving us 1.5. Then when it comes to the UDL, we're going to say half, we said this is always going to act at the center. So half of 0.7 is 0.35. And hence we end up with something like this. So you say this is equal to, you have our moment, which is 5 times, oh, sorry, not this one. I'm talking about, yeah, it's okay. The same one, 5 times 0.7. Then multiplied by half of this is 0.35. Or we can say 0.7 over 2. And plus what? Plus this distance now, which is 0.8 plus 0.8. In other words, what are we even saying? We are saying it's as good as having, here I'll close, it's as good as having 5 multiplied by 0.7 and then multiplied by 0.35 plus 0.8. What does that give us? It gives us 1.15. So this is the combination you see there, 5 times 0.7 times 1.15, giving us a negative result, negative 0.06875. Then on the same point C, we also have another one where we bring back all these numbers, but with an addition of that floating moment, the additional moment, which is the 0.5. So 0.5 added to the final answer we had there. The result is 0.43125. Next is the last one, which is point B there. For the last one, the first thing you may assume is that it's 0, which is correct, but we should always prove that this is correct. That is so with the working. So we have moment is equal to 2.6375 times the whole distance, which is 2 meters, minus 5 times 0.7. So we're saying 5 times 0.7, the force, then, sorry about that, let me pick the other one. 5 by 0.7 multiplied by 1.65. How do you get 1.65? The whole distance between these two is 2 meters. So what you are going to do, the UDO, we said it always acts at the center. So the distance now from here all the way to the far end where the A is, that's the one we're interested in. So what are we going to do? We are going to remove, because we know the distance from here to the far end, this is 0.35, half of 7. So to make it faster, you can just say 2, take away 0.35. Where is the 0.35 coming from? 0.35 is half of 0.7, describing where this is acting. So meaning the distance from the middle to end B, to point B, is 0.35. So since the whole distance from this end to that end is 2 meters, it means to get the distance we want here, we have to subtract this, which is here the 0.35. That's how come we end up with the 1.65. Then again, we are going to add now that moment floating as well, which is the 0.5, because it's also clockwise. So it will behave like this one, the way this one was behaving. So once you enter this in your calculator, you end up with 0 as our answer. And we leave it at that. We leave it there. Then the question is still there, where maximum bending moment, the other part of the question. In this case, our bending moment is maximum at 0.7 meters from B, where we have 0.62125. Okay, yeah. In that case, let's make progress. So here now it's time to draw. So as we decide to draw, we copy the diagram the way it was. At every important point, we drop down dotted lines. And hence, for the shear forces, we start with the horizontal line. And we capture the numbers at A, it's 0. At B, we had negative 0.8625, which goes all the way, it's D to A. So we leave it like that. For the bending moments, we started with A, 0, B, 0.6125 kilonewton meters, C had two numbers. The first answer was negative 0.06875. The second one is where we add that moment which is hanging there. So we end up with 0.43125. And lastly, at point A, at the last point, the answer we found was 0. So then we connect these now with lines, and hence we formed our shear force diagram for the top one and our bending moment diagram for this one now below. Question number 5, describe two assumptions made in the theory of simple bending. Now here I have to be specific that in the theory of simple bending, you do not have 2 or 3. They can even reach 8 of those assumptions. That ensures that the analysis we're doing works out without us worrying about what is missing. One of them is that we expect that the material is uniform. It's the same. It's homogeneous throughout. And also, before and after bending, the plane section should remain the same. It remains plane before bending and also after bending. Then the beam is initially straight and of uniform cross-section. That's why we call these assumptions, because in reality, this is very difficult to achieve. It's not always going to be like that when you check, especially when you look at these components under a microscope as you do your examinations or your investigations. Next is the radius of curvature. We expect it to be larger compared to the dimensions of the beam, just normal, because in some cases, you can find a very, very large one, meaning the lower the bending, the bigger the radius. So this is just an assumption which is normal. But in extreme cases, we may go beyond that. We may easily go against this assumption in reality. So here's our next question. It says, calculate the value of the second moment of area of the axis about the neutral axis of the T section beam shown in figure Q5. Now, this figure Q5 has one catch. We've already been guided as to which neutral axis they are talking about. Neutral axis NA. So these are the dimensions 100 by 10, then 120 by 10. So what are we going to do? We are going to divide it. We are going to divide this into segments. Segment number 1 is this one cutting the bottom part of the T section. Dimensions of portion 1, 120 millimeters by 10 millimeters in thickness. Portion number 2, 10 millimeters by 100. So combined, you have now these two portions there. The other thing, each of them has a distance for the centroid. Portion 1, its length there is 120. So the center of 120 is half of it, which is 60 from the base. So from the base to there, that is 60. Then for section 2, the portion number 2, this one on top, according to what we've cut. For this one, we are going to also say this 10 divided by 2, meaning that our centroid for it is at this point. Now, what are we going to do then? Because half of 10 is 5. And as a result, we are going to agree that the distance from here up to the center is 5, this one. Then this 5 should be added to this, because the distance of the neutral axis for this portion, for all of them, we're measuring along the y-axis, or rather from the x-axis at the base. So it's from there going up. So this distance we have as 120 plus half of 10, which is the 5. So 120 plus 5 gives us 125. That is our bar y. So we're also going to find the areas one by one, just like that. So with that in mind, okay, yes. Let's start with shape number 1. We said the dimensions are 120 by 10, giving us 1,200. Shape number 2, the dimensions are 100 by 10. And when you multiply those two, you end up with 1,000. If you look at shape 1, we said its bar y, its distance along the y-axis to the centroid of the first shape is 60 millimeters. For the second one, the top one, section 2, its neutral axis, its centroid is at 125 millimeters from the base of the whole shape, where we said 5 plus the 120, so we ended up with 125. The last thing we do is just to multiply area by that distance we just determined. So 1,200 multiplied by the 60. 1,200 times 60, our answer is 72,000. The next one is 1,000. So 1,000 times 125 here. We have 125,000. Now, we don't end there. We have to add them up. So in adding them up, you now have this 72,000 plus 125,000. Your value is this 97,000. And remember, our unit is that. This is the summation of area multiplied by that distance for the centroid for each of the shapes. Next is 1,200 plus 1,000. The result is 2,200. For this one also, the unit is here, the square millimeters. Now with this, the first thing we're going to do is to find the neutral axis. Okay. The neutral axis, therefore, or rather the centroid for the whole shape, we invite summation of area times by y, which is this one, divide by the total area, summation of the area. So summation of area times by y is this one, which is 197, divided by the total area is 2,200. So divide by 2,200. So that now our answer is 89.55 millimeters. So now that we've calculated the centroid for this shape, we're now going to calculate the second moment of variance for this one, for this shape, just as it had been requested for us to do. Now, to get this one, we'll pick shape by shape, shape 1 and shape 2, then we add them up. So shape number 1, which was at the bottom, we'll have to, it's normally going to come as a combination. This. Shape number 1, we are going to say B, D cubed over 12. Then added to that, we're going to multiply area times a special kind of y. Just like that. Now, from there, we can now start shape by shape. We'll do the same for shape number 1 so that we get I1. And we'll do the same for shape number 2 so that we get I2. So for I1, our B is 10. Our D, which is the depth, is 120. So 10 by 120 cubed over 12 plus 1,200 is the area times the one we were calling expression by y is the difference between the overall centroid for the shape and the individual centroid for this particular portion. So 89.55 minus 60. And then whatever result comes from there, we square. And we're doing the same even for shape number 2. B is 100. Our D for this particular shape is 10. So 100 times 10 cubed over 12 plus, then we're saying this one at 1,000, but this one, the area is, the other one was 1, 2. This one is 1,000. Then open brackets, we're doing the same thing again. It's the area of the overall the centroid rather, the difference between the distance of the centroid, the bar y for the whole shape minus the bar y for that singular shape, the portion for the top part. So 125 minus 89.55. And whatever result comes from there, we do the same way, squaring. So by doing all that, you end up with 3,752,878.833. Here's my question on this. If you look at the nature of the working we're having here, there are a number of steps, there are these. So you have decimals, and the answer that you get there may not be exactly as what another person may get. So that's very normal. You have some mini differences, especially towards here and after the decimal. That's very acceptable, so you have a range of correct answers. So this is what the question was asking for. And it's in millimeter power 4 or quadrometers. Okay, so now let's make progress. Question number 6. Explain the concept of bending stress. So when they're asking for the explanation of this concept of bending stress, this is where we clearly explain the transition between the tensile stress material under tension and material under compression, and the material in between on the neutral axis that is not subjected to either of the two. So the moment may be on one side, but that is how the material ends up behaving. So you have the neutral axis and you have the actual areas where the material is being stressed. Next one, but be distinguished between long and short columns. First of all, a long column or a short column will fail by crushing of the material because of the same direct stress which may be acting on it. But for a long one, it buckles or simply bends and along its own axis. So that's why this is saying laterally. Before the material reaches the crushing strength, it has to bend. Then we know this is the long column. The other thing is that a short column has a high load carrying capacity for obvious reasons. It will not easily buckle. Oh, okay. So this is it. And occurs at lower varying loads just like that. Then we, okay. Let's now go to the application. We have an elongated long alloy spanning a length of 4,800 millimeters with an external diameter of 45 millimeters and an internal diameter of 20 millimeters. Functioning as a column with one end rigidly fixed and the other end hinged. Calculate the critical backing load using Euler's formula. Assume Young's modulus to be 160 giganewtons per square meter. Let's pick out information given. First, the data. The length of the whole section is 4.8. Diameter of this alloy member. Sorry. The diameter is 45 millimeters, which when you convert, divide that by 1,000. That's how come you see we've written 0.045. Then we also have the inner diameter. Which is 0.02. And then Young's modulus is E 60 by 10 power 9 or 60 meganewtons per square meter. So this time around, they haven't given us a thickness, so we've just been given directly the internal and the external diameters of this member. Now, one thing you realize is that we need to find the equivalent length for this hinged end. So how do you do it? There are several formulas. In our case, because it's pinned at one end and hinged at one end or pinned, then the other end is fixed. So the equivalent length in such a scenario is given by L over root 2. Our length is 4.8, then divide by square root of 2. Your answer is supposed to be 3.394 meters. Taking that into consideration, we will also need to find now the I, which is the second moment of area. So how do we find the so-called I? So in that case, what we are going to do is to make sure that we recognize that it's a hollow member. So pi over 4 in the brackets, outer diameter raised to power 4 minus inner diameter raised to power 4. So pi over 64, and in the brackets, 0.045 raised to power 4 minus 0.02 raised to power 4. So once you compute that, you end up with 1.934 times 10 raised to power negative 6. This is our I. Then let's go to the buckling load. The buckling load is PE is equal to pi squared EI over equivalent length squared. So pi squared times our E is 160 times 10 power 9. I is 1.934 by 10 power negative 6. Then divide by the equivalent length being squared. The equivalent length, we found it to be 3.394. So 3.394 squared. And there is our load. 265,126.12 newtons. Okay, so that's our answer. If you want to convert it into kilonewtons, it will be 265.1 kilonewtons. We'll leave it there for now. These are just end conditions. These are end conditions for various scenarios, both ends, the end or pinned, then one end of the member fixed, the other one free, and the formulas follow like that, including what we're using. Question number 7, describe a bimetallic strip. So a bimetallic strip normally combines two materials with different properties, ensuring that they are put together, combined together, such that when they start heating, whenever there's a temperature difference, they'll both respond to it. And because of the differences, we don't expect to have the same expansion rates. And we definitely make use of that in our mechanisms. So there, they have different coefficients of expansion. Okay, let me just remove this one. Yeah, this one is failing to run away. Yeah, and there, good. Okay, let's move this. Aha, good. A beam of uniform strength and varying rectangular section is simply supported over a span of 4 meters. It carries a uniformly distributed load of 15 kilonewton per meter run. The uniform strength is 100 meganewtons per square meter. Determine the depth of a distance of 1.5 meters from one end. If the breadth is the same throughout and equal to 200 millimeters. Scenario 2, the breadth of the center of the span if the depth is constant throughout the length of the beam and is equal to 150 millimeters. With that information, we can now start planting the data. Beam length, 4 meters. UDL per meter, the force per meter is Newton per meter. Stress in this material, 100 megapascals, which is 100 by 10 power 6 newtons per square meter. This was just left out. In fact, these are the ones I'm saying we can easily correct it because it's not a big deal. So we're saying just a minute. Yes, so there we are. This is the one I wanted. Okay, so with that, I think it should be able to work here. The N we want is the capital one, so we'll do this and put that. Then go there. Okay, now let's pick up the first one. The depth of a distance of 1.5 meters from one end if the breadth, the width is the same throughout equal to 200 millimeters. Now, one thing about the UDL is that to find the reaction, we multiply WL divided by 2. So W is 15,000 times the length of the whole span is 4. Then divide that by 2. So when you say 15,000 times 4 over 2, you end up with 30,000. This is the reaction. And the reactions are the same for both sides of your reactions. For the first one or second one, that's what you get. Generally, that's where we are. Then the question is asking for 1.5 meter from one end. That being the case, then let's invite the moment. Let's calculate that moment. The moment starting from the left, the reaction is normally positive. So 30,000 times that 1.5 minus 15,000 times the same 1.5, but again we multiply by 1.5 over 2. So 1.5 over 2, and then we punch that in the calculator to get 28,125. This is our moment. This is our bending moment for this one. Then bending stress. The bending stress therefore becomes, we said, the stress Y over I, coming from the bending equation. Now, since we know that I is BD cubed over 12 and Y is normally D over 2, then we can just substitute this in the main equation, these two, substituting in the equation for stress. So it becomes M, Y is D over 2. Then we proceed with the I is BD cubed. Sorry, it's supposed to be BD cubed over 12. However, we are dividing, so that's why they have swapped. It becomes 12 over BD cubed. When you cancel, when you are there, you realize this one, in fact, this one, okay. So let me just remove this one, clear there. So it simplifies to 6m over BD squared. That's our stress. And all we can do now is just substitute. So we can do the substituting. So we substitute stress 100 by 10 power 6. Then equals 6 is just like that times our moment M is 28,125. Divide by B is 0.2 times D cubed. Our D is just D, because that's the one we're looking for. So we make it the subject of the formula. Okay, so with that now, we end up with our diameter as 0.092 meters. Okay, so let's proceed then. Part 2. Now this time around, let's find the width, the breadth B at the center of the span if the depth is constant throughout the length of the beam and is at 150 millimeters. So first of all, the moment is 30,000 by 2, because the 2 is coming from the fact that the whole beam is 4 meters long. So the center of 4 meters is supposed to be half of 4, which is 2. So that beam, the force, the 30,000 multiplied by 2 minus 15,000 by 2 times 2 over 2, just ensuring that we follow up the nature of the UDL. Our answer is 30,000 Newton meters. And then we can now find our B. We make B the subject, becomes 6m over stress times D squared. So that's how you answer that. And then 6 times 30,000 divided by stress, which is 100 times 10 power 6 times D squared. Our D is 0.15, so we just square it. Okay, so with that, we can go to question number 8. Question number 8 says define torque. Torque is normally the product of force and radius, turning effect of a force. So that's the formula. Then B says a propeller shaft has an external and internal diameters of 250 and 150 millimeter respectively. Determine power that can be transmitted at 120 RPM. Okay, so given that we are trying to calculate the power that can be transmitted at 120 RPM if the shear stress is not to exceed 80 meganewtons per square meter. Angle of twist of the shaft at the above stated maximum shear stress, given that the length of the shaft is 5 meters. Take modulus of rigidity, which is G, as 84 giganewtons per square meter. So our data, first of all, rotational speed is 120, shear stress is 80 by 10 power 6. Diameter is impolite, it's rather 0.25. Small diameter, the inner one is 0.15. J, the modulus of rigidity, we've just found it, it's 0. Okay, so inner diameter 0.15, outer 0.25. Then modulus of rigidity, J, rather the polar moment of inertia, pi over 32, then D4 minus T4. So we just substitute pi over 32, then 0.25 power 4 minus 0.15 power 4. So from there, our answer becomes 3.338 times 10 power negative 4. Okay, then there we can just do the substitution. We have T over J, which is 3.338 by 10 power negative 4 being equal to 2 times the shear stress. The shear stress is 80 times 10 power 6. Diameter, we're using the outer one, it's 0.25. Okay, so from there we end up with our torque as 213,632. Then we can now compute the power. The power is 2 pi nt over 60. So 2 pi times n, which is 120, times t, the one we're from finding, 213,632. Everything divided by 60, giving us 2,684,578.887 watts. That is the power that can be transmitted. 2, we're looking for the twist angle under those conditions. So we invite T over J is equal to G theta over L. And we substitute. Our T is 213,632 over J, which is 3.338 times 10 power negative 4 equals, on top, our G is 84 by 10 power 9 times theta, which we don't know, divide by the length of this whole member is 5 meters, so that's over 5. Our theta, the answer is here. The answer is actually this one, 0.0381. But these angles are normally not properly understood when you leave them in radians. They're supposed to be in degrees. So for the degree, we multiply by pi over 1/8 over pi, and the answer is 2.18 degrees. Okay, so that is the end of our paper. We look forward to the next one. Just pause there.